In this section, we are going to talk about some elementary properties of the continued fractions. And first, a definition. A simple, continued fraction is a formal expression of the form a0 plus 1 over a1 plus 1 over a2 plus 1 over a3 plus ... I use the word simple here to mean that in the numerators, we require those numbers to be strictly 1. And we will also denote this form by using the sequence of numbers a0, a1, a2, a3, ... with a sub n is a positive integer for n greater or equal to 1, and a0 is a natural number that includes 0. And we also write a0 semicolon a1, a2 all the way through an for the finite fraction a0 plus 1 over a1 plus 1 over a2 plus ... all the way through n minus 1 plus a sub n. And you will see immediately, for example, a finite continued fraction a0, a1, a2 through a sub n is equal to a0 plus 1 over a1, a2 all the way through a sub n. And you give this guy a label 3.1, same as the one in the book. We'll see later that this expression, this form, converges, and therefore it defines it as a real number. And here I should add that the numbers a sub n are called the partial quotients of the continued fraction. You might be curious why we put the word simple in the parentheses here. Simple refers to that the numerators are all equal to 1. If they're not ones, then it is non-simple continued fractions. So here we only deal with simple continued fractions. The following simple lemma we are going to introduce is crucial for many of the basic properties of the continuous fraction expression. So lemma 3.1, as in the book. We fix a sequence a sub n, where n is greater or equal to 0, with a0 in the natural numbers including 0, and a sub n, that is a positive integer for n greater or equal to 1. Then the rational numbers p sub n over q sub n, which is defined to be this A0, A1, A2, all the way through A sub n. And this equation is 3.2. For n greater or equal to 0, with, this is important, coprime numerator p sub n greater or equal to 1, and denominator q sub n greater or equal to 1 can be found recursively from the relation given by the following product of the matrices. This 2 by 2 matrix p sub n minus 1, q sub n minus 1 is equal to the product. First matrix A0, 1, 1, 0. Second one A1, 1, 1, 0. All the way to A sub n, 1, 1, 0. And this is true for n greater or equal to 0. And at this point, you might be curious, what happens when n is equal to 0? So what is p negative 1 and q negative 1? We need to make some stipulations. In particular, we set p negative 1 to be equal to 1 and q negative 1 to be equal to 0, p naught equal to a naught, and q naught be equal to 1. And with the same notation as in the book, this is equation 3.3. So if you plug in those information to the situation where n is equal to 0, this p naught is equal to a naught, p negative 1 is 1, and q negative 1 is 0, and q naught is 1. Okay, so left hand side is equal to right hand side. Good. The first thing that I need to explain is this coprime condition. Of course, this expression uniquely defines this irrational number through our definition in here. But at the same time, we can always rescale Pn and Qn. For example, we can multiply the numerator and the denominator both by 2. And this still gives us the same rational number. But the interesting part is that why the p sub n and q sub n defined in this recursive formula through the product of matrices gives us the coprime pair p sub n and q sub n for each n. Why p sub n and q sub n defined in here are coprime? This is because if you look at this matrix through this product, what do you see? In particular, if you look at the determinant of this matrix, what do you see? The determinant of this matrix is, by our construction, the determinant of this product, which by linear algebra is a product of determinants. But we know that each of those factors is negative 1. So they are just product of negative 1s. In the end, you will get negative 1 raised to the power n plus 1. Okay, so the determinant of this is plus or minus 1. And if you write this out, you will get q negative 1 times p sub n minus q sub n times minus p sub n minus 1 times q sub n is equal to negative 1 raised to the power n plus 1. So this is plus or minus 1. But you know, this guy is an integer, this guy is an integer. And thus, by the Bezo's theorem, you know p sub n and q sub n are coprime. That explains the coprimeness of p sub n and q sub n, defined through 3.3. Okay, now let's start proving this lemma. We'll prove this by induction on the integer n. So let's first look at what happens when n is equal to 0. When n equals 0, suppose you have this relation, this recursive relation 3.3, p0, q0, p negative 1, q negative 1 equal to a0, 1, 1, 0. Then immediately you have p0 equal to a0 and q0 equal to 1. Using this information, you immediately get p0 over 1 equal to a0, which is exactly what is given in the formula in the equation 3.2. So the case when n is equal to 0 is trivial. So the case when n equal to 0 is trivial. And now let's make our induction hypothesis. Suppose for n greater or equal to 0, less than or equal to k minus 1, the equation 3.3 implies 3.2. And this means, suppose you have this equation. You have p sub n, pn minus 1, q sub n, qn minus 1, and this is equal to the product of this matrix from a naught 1, 1, 0 to a sub n 1, 1, 0. Then, after a very complicated computation, when you literally compute what's happening on the right hand side, in the end, the entry you get at the upper left over the entry you get at the lower left, that ratio is precisely given by this, which is the same as the thing we define in here. And you know this thing satisfies this relation, which we are going to use. This is something we are going to use in our induction steps. That is our induction hypothesis. Let me write this down very carefully. Namely, if you have this, which is equal to the product of those matrices, a naught 1, 1, 0, all the way to a sub n 1, 1, 0, you will have p sub n over q sub n equal to this continued fraction. For n is greater or equal to 0 and less than or equal to k minus 1. That is our induction hypothesis. Now here is a very, very important step and a little bit hard to understand. This induction hypothesis actually tells you something more than this. The induction hypothesis actually tells you the following. If what you have is not some specific labels like p sub n minus 1, q sub n minus 1, it's something that looks more general. If you just have those four numbers, four integers, x, x prime, y, y prime, written as a product of k matrices, remember, right here we have a product of n plus 1 matrices, but n is from 0 to k minus 1. So at most, we will have k many matrices. And here we have k many matrices. And now do you see what this induction hypothesis will tell us in here? I'll let you think about it for a while. But I will tell you the answer anyway later. What this induction hypothesis tells you is that x over y is equal to the continuous fraction starting with b1. And why? Because if you look at this carefully, in this equation, we are not actually using any particular relation between p sub n and p sub n minus 1, q sub n and q sub n minus 1. You can safely replace those with four arbitrary number, and as long as this number of product of this number of factors in here does not exceed k, noticing that there are at most k factors in here allowed in this induction hypothesis, you can safely draw a conclusion that x over y is just this number, this continuous fraction, where b sub 1 through b sub k can be any positive integers. And that is what this induction hypothesis tells you. And now if you truly understand this part, the rest of the proof shouldn't be too hard. Now let's continue. Now for the fixed integers, is a naught, a1 through a sub n, as in the hypothesis of the lemma, we let b sub 1 be equal to a1 all the way through b sub k to be equal to a sub k. So we take b sub 1 through b sub k to be those specific numbers. After doing this, we will see x over y is just equal to a sub 1, a sub 2 is equal to the continuous fraction defined by starting with a sub 1 all the way through a sub k. And if the pairs p sub n, q sub n's, where n is non-negative, are defined recursively, as in 3.3, namely if they are defined like this, then we will have that for that given k, p sub k minus 1, q sub k minus 1 by 3.3 is equal to the products a0, 1, 1, 0, a1, 1, 1, 0, all the way through a sub k, 1, 1, 0. But look, what is this part? This part, by our construction above, is x prime, y prime. Look, here we are taking b sub 1 to be a sub 1, b sub k to be a sub k. And we get exactly this matrix with 4 entries is equal to the product from a sub 1, 1, 1, 0 to a sub k, 1, 1, 0. So this is what we get in here. So let's write this down carefully. So this is equal to the product of a naught 1, 1, 0 times this guy. And this product is equal to a naught times x plus y, a naught x prime plus y prime. Here it is x, and here is x prime. And now let's look at p sub k over q sub k. This ratio is a naught times x plus y over x, which is a naught plus y over x, which is a naught plus, so what is y over x here? Y over x here is exactly the reciprocal of this. So what we get from here is 1 over the continued fractions, the continued fraction starting with a1 through ak. And this gives us the continued fraction starting with a naught. Remember, this is our recursive relation for continued fractions, which I talked about right here. And this finishes the proof, because this is what we want for the induction. Starting with k minus 1, we get the result for k. This is what we want.